Welcome to our last day for our integrals units. We are going to look at U-sub using trig identities and inverse trig, and I promise you this is the last methods we're going to look at for U-sub. So to begin, I have two questions that you can try on your own, 1A and B. And you're going to use U-sub to solve for this, so go ahead and try those on your own, and then when you're ready, press play. For question 1a, we are going to let u be cos x because the derivative of cos x gives us sin x back, but there will be a negative associated with it. All we have to do is move it to the other side with du. Then we're going to replace our cos x with u and our sin x dx with negative du. Then we'll integrate 3 to the power of u, which is negative 3u over ln 3, plus some constant because this is an indefinite integral. Then we're going to plug the u back in and we're done. For b, you're going to let u be x squared plus 2. Then you're going to take the derivative of that, which is just 2x. There is no 2 inside our integrand, so you're going to move the 2 to the other side with the du. Now we can also find our new bounds. I plugged in u of 3 into the x squared plus 2 and got 11. I plugged in negative 2 into x squared plus 2 and got 6, so those are our new bounds. Then I replaced the x dx with a half du and the x squared plus 2 with just a u. And don't forget the squared, that was coming from our original function. Okay, now I just pulled the half to the front and integrated u squared, which is a third u to the power 3 by reversing our power rule. Then I simplified the coefficients to get 1 over 6 and then evaluated it. Plugged in 11 into u cubed and also 6 into u cubed and subtracted them. Now looking at integrals involving trig and squared trig. So hopefully these look familiar to you because these are some trig identities that you probably looked at in grade 12 pre-cal. Look at how these are rearranged. So if you ever see tan squared x, you can rearrange it as so. If you see cos 2x and 2 cos squared x, then you can rearrange cos squared x as so. And lastly, you want to rearrange this identity so you have sine squared x. So every time you see cos squared x, sine squared x, you're actually just going to replace it with these identities. Okay, let's start with some easy ones. I'm going to integrate sine x dx. The antiderivative of that is going to be negative cos x plus some constant, because we know the derivative of positive cos x is negative sine x, but we don't have a negative inside our integral, and that's why we count for that when we are finding our antiderivative. The next one, the integral of cos x. This is the derivative of sine x plus a constant. Sine squared x is the derivative of tan x plus some constant. Negative cosecant squared x is the derivative of cotangent x, but we don't have the negative here, so we're going to account for that in our antiderivative. Tan x, well, we don't know what the antiderivative of that is, but I can also change tan x to sine x over cos x. And I know what the derivative of cos x is. That's negative sine x. And then I can replace accordingly from that. You don't want to let u be sine x because that derivative is cos x, but it's not 1 over cos x. So it's always better to look at your denominator to see if that could be your u. So we can do some replacing here. Sin x dx becomes negative du. The cos x on the bottom becomes u. I'm just rearranging. So the antiderivative of 1 over u is ln. absolute value of u plus a constant, and then we're going to replace the u with cos x. And then you're done with that one. Cotangent x is very similar, but cotangent x is cos x over sine x. Now this time we're going to let u be sine x, and then du be cos x dx. And then we're going to do our replacing. So that is du 1 over u, which is ln absolute value of u plus a constant, and our u was sine. And that is our final answer. For G, again, if we want to take the antiderivative, we don't know the direct antiderivative for this one, but we can manipulate this in some sort of way to make it easier for us. I'm going to multiply this top and bottom by cosecant x plus cotangent x. And you're going to see why in a moment. I'm going to simplify this. So we have cosecant squared x plus cotangent x, cosecant x all over cosecant x plus cotangent x. If I let my u be our denominator, we will get a variation for our derivative of that. So if we let u be cosecant x plus cotangent x, if I take the derivative of cosecant x, I'm going to get back cosecant x squared x minus cosecant x cotangent x. And don't forget your dx at the end. And if you take a look at what we have and compare it with our numerator in the original integral, we're just off by that negative, and we can just factor that out. And now we can continue and replace. So our numerator is now negative du, and our denominator is u. This will be negative ln absolute value of u plus a constant, but u is cosecant x plus cotangent x. This one's very, very similar. We're going to multiply it by secant x plus tan x now, top and bottom. You can follow the same sort of process, but if you look at our end product, we got cosecant x plus cotangent x inside of ln. So same sort of thing. This will be ln of secant x plus tan x plus a constant. And we don't need to worry about having that negative, because when you think about the relationship between cotangent x and cosecant x, the derivative of cotangent x is negative cosecant squared x, which is why we counted for that negative. We don't have the same sort of thing for tan x, because if we take the derivative of tan x, it's positive secant squared x. If you want to see the full solution to this, then I would follow exactly the same steps as in G, and you're going to end up with the same result. For I, so since we have a sine squared x, I can do my replacing with this identity over here. So I'm going to replace sine squared x with 1 minus cos 2x over 2. And then we can integrate each term. So this is 1 over 2 dx minus We can pull our fraction to the front because it's just a number. Cos 2x dx. For our second term, we can let u be 2x because we know the derivative of 2x is just 2. And that we can always pull out in the front of the integral. So we're going to let u be 2x, then du is 2 dx, or you can move the 2 to the other side with du. I can integrate this first one right away. This is just going to be a half x. And then I'm going to replace the 2x with u. And we're supposed to replace the dx with a half du. I'm going to move this to the front. Now we're going to integrate the cos u. And that's going to be negative sign, positive sign. The derivative sign is cos. And I'll plug the u back in, which is 2x. That is our final answer. For cos squared x, if you refer back to the last page, we can replace cos squared x with its identity, 1 plus cos 2x all over 2. It's going to be very similar to the last one. So we can separate our integral to 1/2 dx plus a half cos 2x dx. And then we can let u be 2x. du is 2 dx, or we can say half du is dx. The integral of a half is just a half x. We'll integrate cos. This is supposed to be u du. I'm just going to skip a step because we've already done this question. So this will be sine u. And we also have this half from the du from before. Then we're going to replace the u with 2x. And that is our final answer. For tan squared x, again, if you go back to the first page of our notes, we can replace tan squared x with secant squared x minus 1. This one's really easy for us to integrate. Secant squared x is the derivative of tan x. And then the antiderivative of 1 is just x, plus a constant because we have an indefinite integral. This next one is easy as well. We can replace cotangent squared x with cosecant squared x minus 1. The derivative of cotangent x gives us a negative cosecant x. So negative cotangent x derivative will give us positive cosecant squared x. The antiderivative of 1 is just x. Then add the plus a constant. This is our last method, and it is a bit tricky using inverse trig, but it's very useful as well. Here are the following steps for your inverse trig U-sub. You're going to identify the inverse trig formula that the integral most looks like. Then you want to get the constant to be 1. So that's usually this number here. It needs to be 1. Then we're going to write the x part as something in parentheses squared, which is this section, as something squared. And then we're going to use U-sub and integrate. So I'm going to go through these examples with you, and you're just going to follow along and see how it's done using those steps. My first step is to see what this looks like the most. Well, our tan inverse one doesn't have a root sign, so definitely not that. For a secant inverse x, we have x squared minus 1 with an x in the front. And if I look at sine inverse x, we have a number minus x squared. So it seems like sine inverse is probably the one I'm going to be using. Okay, so that's what step 1 was. We're going to use sine inverse x. Step number 2, get the constant, which is this number here, to be 1. That means I need to factor out a 4. So I'm going to factor out a 4. So now I'm left with 1 minus x squared over 4. I can pull the 4 out because the square root of 4 is just 2. Step 3 says write the x part as something in parentheses squared. So x squared over 4 is the same thing as x over 2 all squared. So that's what step 3 means. Now we can assign our u for u sub. I'm going to let u be x over 2. Then du then will be a half dx. And in this case, I'm just going to leave it like that. And we are going to replace in terms of u. So our half dx can replace with du. And this will be 1 minus u squared. This is sine inverse. Okay, just take a look at this identity here. If you integrate 1 over the root of 1 minus u squared du, then you're going to get sine inverse u plus a constant. And then we can replace the u with what x is, and that is x over 2. And we're done with that one. This next one, let's see which one this one looks like. I think this one's clear, it doesn't have a square root sign, so we're going to use the tan inverse one. The first thing I'm going to do is move the 3 out. Sorry, this is missing a dx. Then we're going to factor out the 16. So I'm left with 1 plus x squared over 16. I'm going to move the 16 with the 3 for now. And rewrite my x squared plus 16 as x over 4 to the power of 2. So I'm going to let u be x over 4. Then du is going to be a quarter dx. Or in other words, this could be 4 du is equal to dx. Now I'm going to do some replacing. I'm going to replace dx with 4 du and the x over 4 as u. I can move this 4 to the front and multiply it or cancel out with a 16. So now we're left with 3 over 4 du over 1 plus u squared. So this now here looks like tan inverse once we integrate. And lastly, I'm going to put the u back in. And there you go, we're done with that one. For K and L, it's going to be a little squishy. I understand that. I'm running out of room, but just bear with me. Same sort of steps for K and L. I'm going to see which one that this one will fall under. We don't have a square root sign, so it's probably going to be tan inverse x. And we just have to do a little bit more work because we do have this 25 in front of the x squared, but it's still not a big deal. Okay, so the first thing I'm going to do is factor out that 9. I can move the 9 to the very front of my integral. Now I'm going to rewrite 25x squared over 9 as something squared. So that would be 5x over 3 all squared, because that's equivalent to 25x squared over 9. So I'm going to let u be 5x over 3. Then my du is going to be 5 over 3 dx. I can move this with my du, so that's 3 over 5 du is dx, and I'm going to do my replacing now. So 1 over 9 is still in the front. This dx is going to be replaced with 3 over 5 du. Then I have 1 plus u squared, because 5x over 3 is our u. I'm going to move this 3 over 5 to the front. This would cancel out this 9 and have a 3 at the bottom, so that's actually 1 over 15. Now this part here is tan inverse once I integrate. And then I'll replace that u. And we are done there. Our last question. So this one looks like the secant inverse x, because we have a x in the front of this square root. I'm going to begin by factoring out the 9. Not the 4, but the 9, because it has to be that constant number. Okay, and then our next step is to take that 9 out by taking the square root of 9, which is 3. I'm going to rewrite this 4x squared over 9 as something squared, so that can be 2 over 3x squared. And then now I'm going to replace 2x over 3 with u. du is then going to be 2 over 3 dx, or you could also say 3 over 2 du is dx. You can move the third to the front. So now I'm going to do some replacing. I'm going to move this a third to the front of our integral. And we do have this x over here to consider. So I'm going to rearrange this so I know what to replace x with. So x is going to be replaced with 3 over 2u. Then we have the square root of u squared minus 1. Then our dx is going to be replaced with 3 over 2 du. So our 3 over 2 is just going to cancel out. And this is what we're left with. Now this one, if we integrate this, it's going to be secant inverse x. And then we're going to replace the u, which is 2x over 3. And then we are done.